She did 2 years of master's, first in fundamental and applied physics at Sorbonne University, and then in astrophysics another year in Montpellier. Since 2021, she's working on her PhD between University of Lyon and the European Southern Observatory in Germany with Nicolas Boucher, Gergo Popping, and Michele Ginolfi. She's a multi-wavelength observational astronomer. As we will hear in her talk, she has used different instruments and different telescopes from UV all the way to infrared to look at study the baryon cycle of galaxies at high redshifts. And she's actually submitting her thesis in only 3 weeks. So thanks for being here, given all the stress that I'm sure you have. She'll be joining us later in fall as a postdoc in the astrophysics group to continue her research, but at that point with James Webb data. So it's great to have you here. And with further ado, I'll give the floor to you.
Great. So thank you. And I want to take this moment to also thank you all for welcoming me so well in the past 2 days. I've had a great time. Yeah, so in my research, I'm interested, is that okay? I'm interested in the evolution of galaxies through the perspective of the matter cycle. So to be more precise, I'm interested in the baryonic matter of galaxies. So in this talk, there won't be any dark matter. So here I'm showing you a timeline of the evolution of the universe, where we see galaxies evolving from small density fluctuations to the massive structures that we observe today that are made of baryons and dark matter. So as astronomers, we study galaxies at different epochs in the universe to understand the different stages of the evolution of galaxies. And one epoch that I am particularly interested in is the one that we call the cosmic noon, and it corresponds to the following. So when we measure the cosmic star formation density, so the amount of stars build up in our universe, early universe is on the right, and then today is on the left of this plot, we observe a peak in this star formation. And this peak happened when the universe was about 2 to 4 billion years old. And this is, or redshift 2, and this is the peak that we call cosmic noon. So putting this back into this plot, this is where cosmic noon roughly lies. And this is where I focus most of my work. I also go a bit onward to almost the present day, but not really. Now, so we know that galaxies are not isolated islands like Wright and Kant imagined in the 18th century. They're actually connected to the environment, and it is through these connections that they evolve. So here I'm dividing the evolution of galaxies in 2 main parts, the secular evolution and the stochastic evolution. And as an example of the secular evolution, I'm showing here this famous nearby galaxy, M82, seen with HST, where we see the galaxy, yep, oh, no, sorry, here. So we see the galaxy with the blue colors that traces the stellar disk, and then we see gas outflowing outside the galaxy with the red colors. So the secular evolution of galaxies happens through these gas flows going out of galaxies, as illustrated on this image, but also and mostly through gas accretion so the gas going into galaxies. So I'll come back in more details on this picture, the secular evolution, later on. And the other category I'm making here is the evolution of galaxies through more stochastic and dramatic physical processes, such as galaxy mergers. So here I'm showing you an image from James Webb of ZW296, which is a pair of 2 galaxies in a process of merging here. But studying these 2 aspects of the evolution of galaxies can be quite challenging with observations because gas flows in galaxies are intrinsically faint, and galaxy mergers can be difficult to identify. So in my thesis, these are the 3 projects that I explored and that I will detail today. So first, I studied the impact of gas flows on the baryonic properties of galaxies. And in particular, I focused on the stellar mass, the star formation rate, and the metallicity of galaxies. So the abundance in heavy elements traced by oxygen. So if I go back to this picture that that illustrates this gas outflowing and inflowing in galaxies, what gas regulator models tell us is that the evolution of galaxies is driven by a balance between pristine gas accretion coming from the surrounding gas that we call the CGM, the circumgalactic medium, star formation occurring within galaxies, and then gas being reprocessed and ejected outside of galaxies as a result of supernovae and AGN activity. So as a reflection of this equilibrium scenario, we find galaxies on scaling relations, such as the main sequence and the mass metallicity relation. So the main sequence is the relation between the stellar mass of galaxies and their star formation rate. And the mass metallicity relation is the relation between the stellar mass and the metallicity of galaxies. And simulations predict that galaxies on the upper part of the main sequence are the result of gas accretion, and on the lower part of that relation as the result of gas depletion. So the thought is that gas being accreted onto galaxies feeds them, it brings them fresh material to form stars, therefore we find them on the upper part, while outflows are removing gas from galaxies, so therefore they don't have enough material to sustain their star formation. And as for the mass metallicity relation, simulations predict that galaxies with strong inflows would be on the bottom part of this relation, because that gas that is being accreted onto galaxies is pristine, it's metal poor compared to the galaxies themselves. So therefore, it also dilutes the metal content of galaxies. So now the goal of my first PhD project was to test this with observations. Can we actually observe these predictions? However, what I was saying before is that gas flows and CGM where gas flows are happening is quite challenging to study with observations because they're quite faint, but we have ways around it. So a technique that is commonly used, and the one that we used in our megaflow survey, is the background source technique. And the way it works is the following. So we observe a distant quasar, and as the light reaches us, along the line of sight, if there is intervening gas, this gas can be absorbed, and we see this as imprints on the spectrum of the quasar in the form of, in the case of the megaflow survey, magnesium-2 absorption lines. So then when we have these quasar galaxy pairs, what we can do is to classify them according to their azimuthal angle. So the azimuthal angle is the angle between the location of the quasar on the sky, to the parent location, and the major axis of galaxies. So if we see that the line of sight is close to the minor axis, we're likely probing outflowing material. So we classify this as an outflow selected galaxy. On the other hand, if the line of sight is close to the major axis, we're likely probing accretion of gas. So we classify this as an inflow selected galaxy. I forgot to mention it, but all of that is happening with MUSE observations on the VLT. So once we have these samples of outflow and inflow galaxies, we can look at where do they fall on these scaling relations, but we need to build these scaling relations first. So to do so, we use around 319 galaxies at redshift 0.35 to 1.4, with stellar masses ranging from 10 to the 7 to 10 to the 11 solar masses, observed with MUSE within the megaflow survey. So we have a parent sample of 370 galaxies with which we can build these scaling relations. Then we have 21 galaxies that are showing inflows or outflows, observed with MUSE, but also X-shooter to push to the higher redshift part of the sample. And then we also build a control sample from the parent sample, which is a sample of 26 galaxies with no measured gas flows. This way we can compare the gas flow sample with a sample of galaxies with no gas flows. And for all these almost 400 galaxies, I measured the metallicity and star formation rate with optical and near-infrared emission lines. I would say one of the strengths we have here is that we're measuring the metallicity with several tracers simultaneously to break the degeneracies. So in the end, we have our scaling relations that we are building self-consistently with the gas flow sample. This is to ensure that when we look at the location of these gas flows, if we see any offset, this is not due to systematics or calibration differences. So this is the first result. So on the left, what you see is the main sequence, color-coded with the redshift. And I highlighted with blue squares the inflow galaxies. And as you can see, they're all located on or above the zero line. So they're associated with elevated star formation rate. We can quantify better the significance of this by looking at the residuals. So this is what I'm showing here on the right. So now on the y-axis, what you have is the star formation rate minus the fit we found for our main sequence. And you see that the inflow galaxies, so again, these blue squares are on or above the zero line. We also ran a KS test to compare the distribution of these inflow galaxies with the control sample that is marked with the yellow markers. And we found that the distributions are different with a significance of 78%. So this is just above 1 sigma. So it's not a statistically robust result, but we are finding a tentative trend here, confirming the gas regulator predictions. Then here, I'm showing you the mass metallicity relation, so metallicity on the y-axis, and the color code shows you the star formation rate. So essentially, you're looking at a projection of the fundamental metallicity relation. And you can see here that most of the inflow galaxies are on the bottom part of this relation. So these galaxies are in agreement with the picture I was telling you before, where the gas that is being accreted is diluting the metal content of these galaxies. But also something we see is that at a fixed stellar mass, these galaxies correspond to a high star formation rate. So again, in agreement with the picture I was telling you about. And again, when we look at the residuals from this relation, so this time I removed the fit from the fundamental metallicity relation. This is what we find. So you see that the blue squares are now all over the place. So they're not showing any preferred location. And so this shows us that the dilution of the metal content of galaxies and the enhancement of star formation rate are happening at the same time. And what you see here that I highlighted with this circle is that all the outflow galaxies represented with the red triangles are on or above the zero line. So they're associated to metal-rich galaxies. Again, I ran a KS test to compare the distribution of the outflows with a control sample. And this time we found a difference in the distributions with a confidence level of 98%. So this is almost 3 sigma. So one last point I would like to discuss here, going back to this drawing of the background technique, is that we're measuring gas flows with absorption lines at a certain distance from the galaxy itself. But the properties we're measuring from the galaxies, we measure them through nebular lines that are sensitive to less than 10 million years of fluctuations. So if we take a cloud of gas that is traveling at a typical velocity of 200 kilometers per second, and this cloud reaches a distance of around 50 kiloparsecs, and these are all numbers typical of our sample, it would take around 250 mega years for this cloud to reach that distance. So in other words, it means that there might be a time delay between these two points. So outflows could be related to past star formation in the metallicity. while inflows could be related to future metallicity and star formation rate. And recent cosmological simulations are saying that the scatter around these relations that I'm studying here is dominated by very long time scales of 1 to 10 gigayears. And if this is the case, then we should observe fluctuations on much shorter time scales on the CGM of around a few 100 megayears. And with our results, it seems that we are observing these timescales of a few 100 megayears. So our results are also supporting these long timescale scenarios. Okay. Yeah, so these are the take-home messages from this first project. So we derive our own main sequence and mass meta simulation at redshift 0.35 to 1.4. We found a tentative trend for galaxies with inflows in the main sequence, finding them associated to elevated star formation rate. We found a tentative trend for galaxies with outflows in the fundamental meta simulation, finding them associated to metal-rich galaxies. And overall, all these results are in agreement with gas regulator models, and they tend to support the long timescale fluctuations around these relations. So now I'm going to move on to my next PhD project, which is actually still ongoing. So it's today is the first time I'm presenting this work to an audience. And here I'm moving from the ionized gas that I was studying before to the molecular gas. And it is crucial to understand the molecular gas of galaxies because this is the fuel for star formation. So it allows us to better understand, in the end, the global cosmic star formation. So again, I'm going back to this picture where I was telling you that gas flows in and out of galaxies. And something that we might expect as a result of gas flowing out of galaxies is metal-enriched gas surrounding galaxies. And this is further supported by observations in the local universe, where we do observe molecular outflows. So to trace metal-enriched gas, we typically use submillimetre observation. So we're moving to a different part of the spectrum. And we use different carbon emission lines to trace that metal-enriched gas. But once again, the challenge here is that extended faint gas, molecular gas or metal-enriched gas, can be very faint. And these outflows that might bring this gas outside of galaxies are also faint. So the method we're using here is to use stacking and to bring the sensitivity limits down so we can pick up faint signals. And in fact, recent studies also using stacking are finding evidence for metal-enriched gas surrounding galaxies. So here I'm showing you an example of the first identification of metal-enriched gas surrounding normal star-forming galaxies. But this is at a much higher redshift. I think this was above redshift 4 or something. And you see that the C+ line, which is shown with the red contours, goes to scales of around 10 kiloparsecs. And it also goes way beyond the background image, which is the HST image tracing the stellar component of galaxies. And even more recent studies are also using stacking, but this time of CO observations of AGN host galaxies at cosmic noon. And they also find extended emission. So what they're showing here is the surface brightness radial profile of the CO emission in brown. And when we compare it with the beam, so the PSF of the observations, which is the blue line, you see that the emission extends beyond. So this is not just a simple point source. In this work, they are resolving faint emission beyond the beam. So these are very exciting results, but as any work, they come with their own limitations. And I want to point out 2 limitations here. And these are also the limitations that we see in the literature so far. One is that the C+ emission line that a lot of people in the submillimetre community use because it's so bright and so more easily detectable. The issue with this tracer is that it doesn't trace one single phase of the gas. It traces the multi-phase of the gas. So we cannot actually relate the molecular gas content using this line. We need actual we need CO observations, ideally low J transitions, to properly trace the bulk of the molecular gas of galaxies. And the second limitation here is illustrated with this second paper here, is that most studies so far focus on the extreme objects in the universe, so the AGN host galaxies, protoclusters, or mergers. And so the question that we are trying to answer in this work is, can we observe this molecular, so not just metal enriched, but molecular gas around normal star-forming, main sequence star-forming galaxies at cosmic noon? And the reason why we're asking this question and why it's important to focus also on more typical main sequence galaxies is because these are the ones driving the bulk of the star formation density. And if we do observe extended molecular gas, then can we also find signs of outflows that could explain that this is outflowing gas entraining the molecular gas to the surroundings? Yes. So to do that, we use a sample of 26 main sequence star-forming galaxies at cosmic noon that were published in Valentino and collaborators in 2020. And we stack them. So this sample is at cosmic noon. The galaxies have stellar masses ranging from 10 to the 9.5 to 10 to the 11.5 solar masses. So we're really probing typical main sequence galaxies. And for all these galaxies, we have multiple CO transitions, but in here, I'm focusing on the CO221 emission that I observed with Ivanna and then 3. And all these galaxies are also in the cosmos field. So we have a broad coverage in wavelength, allowing us to probe the properties of the sample. So this is a first result, which is the stacked intensity map. So here I'm stacking the 26 individual intensity map of the CO221 emission. And so you see that we have a clear detection in the center. It's a bit difficult to see if there is faint emission going beyond the beam. So we further investigate with the radial profiles, as I was showing before, with the work of Gareth Jones. So here in purple, I'm showing you the radial profile of the CO221 emission. And when we compare it with the beam, which is the beige line, you see that we are resolving faint emission beyond the beam. And actually this emission, so the pink line here that I'm showing is the noise level of my map. So we know that anything that goes below this noise level, we can't really trust it. It's not detected emission, it could just be noise. So within this noise limit, it looks like the CO221 emission is extending to scales of around 1.8, 1.9 arc seconds, which at the median redshift of our sample, which is 1.3, this gives us an extension on physical scales of around 16 kiloparsecs. But of course, the emission that I'm showing here in purple is the result of observations, which themselves are intrinsic emission convolved with the beam. So I also deconvolved this CO221 emission, and I'm showing this with the gray line that I hope you can see, to really understand what is the actual physical extent of the molecular gas of these galaxies. And here, the extent seems to be around 12 kiloparsecs or 1.3 arc seconds. And then very briefly, to show you, we tested the systematics of our sample to understand if it's just a handful of galaxies that are driving this trend that we're observing, or if it's really a common feature of our sample. So I did bootstrapping on these galaxies. And this is the result I'm showing here. So every white line is one iteration of the bootstrapping, and then the purple line is the median of the bootstrapping. And so this shows us that really we are detecting extended CO emission as a common feature of our sample of star-forming galaxies at cosmic noon. Then further, I investigated the different properties of our sample in different bins. So I redid the stacking of the intensity map and then the corresponding radial profile for different bins of different properties. So on the top left, I'm showing the stellar mass bin. So I'm making 2 bins every time with the low and high. On the top right is the infrared luminosity, then it's the specific star formation rate, and bottom right is the distance to the main sequence. So we have, anything that is within the scatter of the main sequence, we call it main sequence bin, and anything that is above the scatter is the starburst bin. And here we can't, within the errors, we can't really see any deviations or like a clear property bin that shows us a difference. But what we do observe is that it looks like there is resolved CO emission, no matter what bin we're looking at. So now that we know there is resolved faint emission beyond the beam, can we find signs of outflows that could explain why we observe this? So to do that, I stacked the CO2-1 emission line and I searched for broad wings. So what I'm showing here is on the two panels, it's the same spectrum in the background. It's the stack of the 26 galaxies. On the left, I'm trying single Gaussian fit, and on the, wait, yeah, on your left, no, on your right, here, I'm showing single Gaussian fit, and here I'm showing a two Gaussian fit. So there's a broad component. And the goal here is that if the fit is improved when including a broad component, this would show that we are finding hints of outflows. But as you can see in the residuals, the bottom panels, there is essentially no difference. So we are not detecting a very prominent molecular outflows here. But what we do observe is this excess of flux at the negative velocities. And actually, then I repeated the same exercise of stacking per galaxy property bin. This is what I'm showing here. So it's a bit of a busy plot. So I tested, again, single and two Gaussian fitting. It didn't change anything. But what I hope you can observe on this plot is that there is this excess of flux at negative velocities in almost all the bins. And so this is very much ongoing work, but our current interpretation of that is that this could be actually a sign of outflows, because the redshifted part of the outflow could be, so the one that is going away from us and the galaxy could be optically thick. And this is why we have this asymmetry between the negative and the positive velocities. So the take-home messages on this project is that we are observing CO2-1 faint CO2-1 emission beyond the beam. So we are resolving extended emission out to 16 kiloparsecs in the observed emission and deconvolved out to 12 kiloparsec. We don't find a clear difference when we look at the different property bins for this extent. But we do observe the presence of a tentative blue bump in the stacked spectra of these galaxies. So overall, we find an extended molecular gas as a ubiquitous feature of these star-forming galaxies at cosmic noon. And here I put extended in air quotes, because of course the next step, and the one that all of you suggested me at some point when we talked about this, is to also look at the stellar component of these galaxies to understand, are we probing CGM scales with these 12 kiloparsecs, or are we probing the galaxy scales? So that would be more ongoing work for later, to stack the optical data of these galaxies and see if it matches the molecular extent or not. Okay. So this is the last project I'll present today. And this was actually a completely unplanned project in my PhD, because it happened when I was reducing the ALMA data for the stacking project. I was looking at every galaxy, and then I found a bit of an odd case. And this weird case in the ALMA data turned out to be a massive dust-obscured galaxy merger at cosmic noon. So this special case allowed me to go back to a very basic question, because I had never worked with galaxy mergers before, which is, how do we identify galaxy mergers? And so the method that people use up to today is to visually inspect rest frame optical and infrared data. And here I'm showing an example where you see they identified different components of the galaxy merger. So this means that to identify galaxy mergers, you need to see all the components of the merger. And this is the merger that we identified. So it doesn't look like a merger, right? Because this is the HST image, and you only see one single star-forming galaxy, maybe you see a tail there. But when we look at the ALMA data that I'm showing on top of that HST image, this is what we see. So now the blue contours are the CO2-1 emission. And you see that they cover the HST bright galaxy, but most of the emission, the bulk of the emission, is peaking right up there when we don't see anything in HST. And when we look at the dust continuum, which is what I'm plotting in beige, you see that it aligns again where we don't see anything in HST, and it aligns with the bulk of the molecular emission. So this revealed another galaxy that was hidden there by the dust, and that is actually merging with the one that was misclassified as a single star-forming galaxy. And as I was saying before, this galaxy is in cosmos, so we have different observations at different wavelengths. So here I'm showing you different panels where you see the HST galaxy with the white contours, and then the dust obscured galaxy traced by the peak of the ALMA contours. And so you see that in the KS band, we actually see the two blobs, and then corresponding to the two galaxies. In the Spitzer data, it's just one massive blob, but that's due to the resolution of these observations, but the emission does cover the two galaxies. And then in the VLA data, so the radio data, only the dust obscured one is picked up. So with this multi-wavelength data, we're really sure that this is a galaxy merger, and we can go one step further and dig into the baryonic properties of these galaxies. So we performed SED fitting on the two components, and we put them in a context of main sequence galaxies to see if we see typical behavior of mergers in their baryonic properties. So I'm calling north the dust obscured one and south the HST bright one. So here, what I'm showing you is the main sequence that we've seen before, where you see that both galaxies are quite massive because they're both above 10 to the 5 solar masses. And north, which is the beige dot all the way up there, is extremely star-forming. So they're both star-forming galaxies, but the dust obscured one is really the one who has a lot of star formation going on. Then I looked into the depletion time of these two galaxies. So the depletion time gives us tells us how fast these galaxies are using their molecular gas to form stars. And you can see that north is almost half a deck below the median of star-forming normal main sequence star-forming galaxies I'm showing with the line. So it's really fast in forming stars. And then I looked at the gas fraction. So this tells us how much molecular gas is still available to form stars compared to the stellar mass that is already formed. And you see that compared to typical main sequence galaxies shown with the line, these two galaxies have relatively or like modestly high gas fractions. So I want to note here that for south, so the HST bright galaxies, we only have upper limits for the molecular gas, so that's why it's two arrows. So maybe it is a bit different in reality, but it looks like both galaxies have similar gas fractions, and yet they show quite different star formation activity. So whether this is due to the merger that is triggering these galaxies in different ways, or if it's because they were already different prior to the encounter, we can really tell with these observations. But that brings me to the take-home messages from this project. So using ALMA observations in CO, we were, and dust continuum, we were able to reveal a dust obscured galaxy at redshift 1.17. These observations with the ancillary data that we have show that this dust obscured galaxy is actually merging with another galaxy that was previously identified. And these two galaxies show overall properties, baryonic properties that are consistent with mergers, enhancing their star formation. And I think the natural question that comes after a work like this when you study one system is how many are like this out there? How frequent is such a system? And here I'm showing you the fraction of major merger as a function of time or redshift. And you see that at the redshift of this merger, which is 1.17, we should have 10 to 20% of galaxies in this merging phase. But all this work, all this literature is based on optical near-infrared data. So it could be possible that we are missing some of these mergers that are simply dust obscured. So to give an overall conclusion to my PhD work, with the first project, we found the first tentative observational proof of the correlation between gas flows and the baryonic properties of galaxies. With the second project, we are finding extended molecular gas. Of course, this requires more work to understand physically what does it mean, this extent. But it seems to be a feature that is common to all these typical star-forming galaxies at cosmic mean. And with the last project, but I think overall with all this work, I think what we are showing here is that we really need the multi-wavelength approach to get a proper understanding of galaxy properties, because they show very differently at different wavelengths. And I'll leave you on the outlook of my future work that I'll be doing here with Irene and James Webb Data, where naturally I think we can investigate, thanks to MIRI, the fraction of these dust obscured mergers, and also investigate the dust and nebulosity properties of galaxies. Thank you.
Thank you, Ivanna. Very interesting results and definitely a lot of prospect for future work. Question.
Hey, really nice talk. I wonder, this blue bump, what is the nature of it? And is it caused by, or is dominated by one of the, or a couple of the galaxies you doing the stacking? Did you do some kind of jackknife thing?
Yeah, I didn't do that with when I do the property beams. That is a good suggestion to do jackknifing to test if this bump is always there. What I didn't show here is that when I do the stack of, the full sample here, I did do bootstrapping and the bump is always there. And yeah, the origin that we find to explain that is that if you have your galaxy here and there's outflow coming in and out, out of it, one that is coming towards you and one going away from you, the part that is going away from you, which is the redshifted part, could be optically thick because of the galaxy.
So it's obscuration just
by
that.
Yeah, exactly.
Optical depth effects.
Yeah, exactly.
Very, very nice talk. So I have two questions. The first one is about the merger.
Yeah.
So why do you know that it's indeed a merger and they are not in the line of sight? Is because of the redshift?
Yeah, it's the same redshift.
Okay.
So the AMA observations, it's the same redshift and they cover both.
Okay.
And then when you look at the different wavelengths, you see that in this one, both appear, like you have two bumps corresponding to the peak of HST and the peak of AMA. In the VLA, you see the one that you couldn't see before that corresponds to that one. So that's what telling us, and also, yeah, same redshift.
Okay, and the other question is about when you have done the stacking of your 26 galaxies, and you show the radial profile, you mentioned that you have done some bootstrapping. You know if the result is dominated by some subsample of the galaxies or is a general thing, right?
Yeah.
So can you explain in more detail what you have done?
Yeah, so by bootstrapping here, what I mean is that I'm remaking the intensity map 500 times, but every iteration I'm removing 30% of the sample randomly. So I repeat this, and every white line is this 500 iterations. So you see that, yeah, even within the scatter of the bootstrapping, it's always.
So in each interaction, you remove
30% of the sample.
30%.
Yeah.
Okay.
Yeah, we try with 10, 20, 30%, and this is always there. Of course, the scatter is bigger when you remove more galaxies because the noise goes up. Yeah.
Okay, thank you.
Very nice results. So about the merger system, in fact, what you obtain, I guess, with IRAC data and with the K-band data is that the hidden component is more massive, quite massive, 10 to 11 solar masses. Normally, the stellar mass of these very dusty galaxies is very hard to calculate and with low uncertainties. So do you have any kinematic information from the ALMA data telling you something about the mass, the dynamical mass that is hidden there?
So I'm not showing it here. We looked at the, so when we have the spectrum of the CO221 line, we also have the spectrum of the CO524 lines. And in the CO524 spectrum, you see two peaks. So you could expect that one peak is one galaxy and the other is the other galaxy. But actually, when I create then the intensity map, only integrating one peak or the other, it shows quite a complex system. So there's no clear, there is no clear association of one peak to one galaxy or to the other. But it's done. It's like it's tentative results because the resolution even of the ALMA observations, they are, as you can see, it's not resolved. So we have to make assumptions on how we separate these two galaxies. So we can't really do proper kinematic analysis. Yeah.
So regarding to this merger, do you know if the galaxy one, the more massive one, was placed like the kind right redshift and mass in the Ultravista catalog?
Sorry, can you repeat?
Like, was it identified as a proper redshift in the Ultravista catalog, or was it misclassified?
Yeah, I didn't check the Ultravista catalog, but I would assume it wasn't classified. Because in the Valentino paper where this galaxy comes from, they flagged this as a special case and then they just discarded it. And then when I looked into the Cosmos catalogs made by John Weaver, this galaxy doesn't exist. And then there's also a catalog by Shaw and Jean. It's called the Super Deblended Catalog of Cosmos, where they're supposed to do this, they blend the IRAC data, and this galaxy is not in there. Okay. So I don't know if it's just because it was too messy, so they put it to the side for later. But yeah, it wasn't identified before.
Thanks.
Thanks a lot for the talk. In the second project that you studied the extension of the molecular gas, you said that you have like a normal main sequence galaxies. Have you compared the extension that you obtained with other works of more extreme galaxies or galaxies in protoclusters?
Yeah, so the works I showed at the beginning, the introduction, showing. Yes, so I think we can't really compare with C+, because again, multi-phase, so you can't really know what you're comparing. There are some works on CO, like the one I'm showing here. I only looked at it actually today to compare the extent. And here, if you compare the CO emission line, like the CO radio profile, it goes out to, I don't know, 15, 16, no, not 15, sorry, 13, 14 kiloparsecs, I would say. Otherwise, after that, the error bars are just too big. Then the intrinsic radio profile, which is their black line, is more like 7 kiloparsecs, I would say. I only looked at it like just an hour ago, so I'm not sure what to think about that. But yeah, because these are galaxies at cosmic noon as well, so it's more comparable. Because if we compare to CO observations at I don't know, redshift 6, we're probing very different scales. So this is more comparable to our work. And yeah, the extent is smaller, right? If you compare, I'm finding things around above 10 kiloparsecs, while the intrinsic here is less than 10 kiloparsecs. I'm not sure how to interpret that, because these are AGN galaxies. So maybe you would expect that they can bring gas further, because we see these gigantic radio jets of AGN galaxies. But I don't know, because it's the molecular phase. Maybe it's different. Maybe the AGN actually destroys the molecular. I'm not sure. I'm not an AGN expert. Yeah.
Other questions online?
There are two additional questions on Zoom. And the first one is, did you use a specific software for the stacking of data cubes? And the second one is, have you thought to expand your study to other environments, such as cluster or cosmic voids, to maybe link what you observe to the specific environment?
I didn't use any specific stacking tool. I stacked myself. The second question was on different environments, right? So no, I didn't think, I mean, this is definitely something possible. I'm not sure if we can do that with CO at cosmic noon for different environments, how it would look like. I don't know if there are observations that are available on that as well. Because, yeah, observing CO at cosmic noon can be easily quite expensive with ALMA. So I'm not sure if there are observations that are already ready to do that. But that could be something to explore, yes.
Maybe you can say a little bit about the stacking technique you're using, because I know you're spending a lot of time on that.
Yeah, it's quite simple in a way. So yeah, things that are important when doing stacking is to make sure that you're stacking detections. So I have a signal to noise limit below which I don't go, because if you include non-detection in your stack, you might be just including noise, and then features you see are just noise related. They're not actual physics. Another thing to look out for when you do stacking is to align things. So when I'm creating my stack map here, I create the individual maps separately. I reduce them in the same way to be sure that I'm not including assumptions that are different for each galaxy to another. So it's the same reduction for all my galaxies. And then you need to make sure that they are well aligned, so that when you stack them, if you see features outside of the center, it's not just because you misaligned in your stack. So this is something I also look out for. I didn't show it here, but I also did stacking of the cube. So here, what I'm showing is first I reduce my galaxy, so I clean the cube. Then I create the intensity map for every galaxy, and then I stack the intensity maps. But then I also explored stacking the cube first. So I have the cubes of every galaxy, then I stack the cube, and then I collapse my cube to create the map. And it shows similar results. So it shows that going from one way or the other shows similar results.
Thank you for the talk. Related with the stacking analysis, are you detecting individually the galaxies?
Yes, they're all detections.
Then the centroid is well defined for each of them.
The what?
The centroid of the galaxy is well defined.
Yes. So I only take, I think my threshold is a signal to noise of 5. So we have detections for sure. So these are quite bright galaxies. And yeah, I take the peak of the emission.
Then
to find the centroid, yeah.
But the error that you had there, because you are in 5 sigma to calculate the centroid, could be affecting this extended emission on that you are finding?
Maybe.
Oh no, you thought it about that, because like if you are not centroiding very good the galaxy, this could be affecting. You have a low number of galaxies that is 26, then maybe it could be affected by some of this centroided uncertainty that you will have there.
Yeah, I don't know how much it would affect. So I looked also at the emission line, the CO emission line of every galaxy. For some of them, it's less clear, but for the vast majority of the 26 galaxies, we have a clear detection. So I'm pretty confident in the centroid that we are using.
Any other questions online? Okay, if not, let's thank Ivanna again.
I don't know how to delete it. So I'm leaving it there. I'm trying to see in Spanish. Which one is me?